Hey, okay, welcome here. We're in the lab. It's the end of week number 3, so we're Wednesday here, and we are on lab number 6 here. And so it's our last lab on mechanics. And so if you want to look into your lab manual to page 41, it'll look something like this. And this is the one I was referring to when I was talking in the lecture about Chapter 8, that the two real hard things, actually there's a lot of hard things about rotation, but the two biggest hard things is to understand torque and also to understand rotational inertia a little bit better. And so this lab has 2 parts. Those 2 parts are hopefully going to help. Part 1 is going to hopefully help you understand rotational inertia a little bit better. And part 2 down here, this table, is hopefully going to help you understand torque a little bit better. And since you've already hopefully seen the lecture from class, hopefully you got a good idea of what's going on. And before I actually talk about the equations and the chart, I think it would be appropriate for you to actually see the equipment this time. So I'm going to come around to the front here and put the equipment on camera here so you can kind of see what's going on. And this is the idea. If you can see here, there is a string that is tied around a pulley down here. And that string right here, if I just kind of, well, wind it up a little more. That string is going to do the tugging, if you will, that supplies the torque. So the torque is going to come from the weight that is hanging here together with the lever arm from this pulley, and that's going to supply the torque. That's why in part 2, we can go ahead and tie this string onto these different pulleys. Each pulley has a slightly different radius, and hopefully what you will observe in part 2 is that the torque will change. And this is a way of showing you that torque depends upon radius as much as it depends upon the force. So part 2, we won't change the force, but we will change the radius. Now, if I let it go, you can kind of see it in action. Again, this little weight, together with that lever arm, is supplying the torque. That's making this whole thing rotate. And when I say this whole thing, let me stop it. This thing is made out of really 3 pieces. This big, long aluminum piece is kind of the stand. I won't really do anything with that. But these weights can slide out, and then I can lock them in at different locations. And so this is part 1. Part 1 is to then move the weights, and we're going to start with them in close, and we're going to move them out, and then of course use the motion here with this weight, which is supplying the torque, and figure out then what is the rotational inertia of this contraption. And hopefully you will see that as the weights move out, the moment of inertia, or the rotational inertia, gets bigger and bigger and bigger. And more than that, as I said in class, it goes up like the square of the distance. So let me kind of set this up for our first measurement, and then I'll go to the board for a little bit. But our first measurement, we're going to be asked to start with the weights in kind of close. It says 3 centimeters. And so right now, the center of each of these squares is 3 centimeters from the rotational axis. So the rotational axis is about where my index finger is right now. And then 3 centimeters over is the center of that square. And 3 centimeters this way is the center of that square. So when this thing spins, I would say that those 2 masses are 3 centimeters out. And of course, it'll rotate from this string and this little weight. Let me point out this little weight is 20 grams, and so we're going to need to know that because that'll be the force that goes with this torque. Now, we'll come back and start our measurement, but let's do some board work here. Because if you look on the top here of page 21, you will see 4 equations that at first may not look very recognizable. But I think 3 of these 4 you will recognize, at least if I talk about them. Watch, let me put them over here. The first equation says A, for acceleration, equals 2h over t squared. Now, that equation actually comes from this one. Distance equals 1/2 at squared. And so if you bring the 2 to the other side, and then divide by t squared, but if you also are talking about something going downward, you might call the distance an h for height instead of distance. And that's what we're going to do. We are going to, and let me put a little comma here, measure how high that little 20 grams that I just showed you is above the floor. We're going to also measure then how much time does it take to go to the floor. Then what I'm going to ask you to do is to get out your calculator and find that acceleration. Now, let me just kind of jump over to the middle board here and put what will kind of look like your table. And so there's the h in centimeters and your time in seconds. And those are going to be the raw data. Those are going to be the 2 pieces that I measure. And what you'll do, and maybe a picture of our equipment might help. So here's the string going over the pulley. And here's the little mass here, which, as I said, is 20 grams. And so if I start with it some distance above the table, and I measure the height and the time, as I said, this first equation will allow me then to calculate what is the acceleration. And I should call that now the translational acceleration of that object going down, because that object translates. That object doesn't rotate. Now we're going to get to the rotating object in just a moment, but this first step really has nothing to do with chapter 8, but it's needed, as you'll see. All right, so in a minute I'll hook those up. Continuing on with our equations, and this is the equation that you have not seen, so I'm just going to give it to you. But there is a mathematical connection between the translational acceleration of this weight going down and then this string, which is then wrapped around this axle that then has these square weights up here. And so as this goes around, this is going to have an angular acceleration. And so there's a connection, because of the string, between the translational acceleration of this and the rotational acceleration of my, what shall I call that, the platform, the base. Well, I'll go with platform, the platform that holds the square weights. Okay, and then that mathematical connection is this. It is taking the A and dividing it by the R. And let me point out then, the R is the radius of where this string is wrapped around. And even though I haven't proven that equation to you, because there's so many other things I better show you, I think you can at least get a gut feeling. Yeah, that makes sense. There's a connection. Because the string is connected around a pulley of radius capital R, this capital R, must be the mathematical connection between the angular acceleration and the translational acceleration. And yes, it is. And so in this little chart right here, what you're going to get is once you get the translational acceleration, your next step is to get the angular acceleration. And so that's the first two equations. So I'll say it again, because what I'm going to do with you is measure height and time. So I'm going to fill in this part of the table. But then I'm going to have you get out your calculator and then calculate the translational acceleration, and also get out your calculator and get the angular acceleration. And so that's what these first two equations are. Now, the third equation you've seen, it may not look like it at first, but let me just remind you, that's the equivalent to a T in the Greek alphabet. That's our tau, that represents torque. And they've got a little formula here that says mg capital R. Now, this from class, we learned that the torque, and we wrote it as little r times F. And so I hope the little r doesn't confuse you, because we're going to use the little r for something else in a moment. And so I want to stay away from the little r, even though we used it in class, because again, we're going to use a little r for something a little different later on. Okay. So the R, the capital R, as we already mentioned, is this torque lever arm, or what your author calls the torque radius. And he gives a spot for you to write down that number. So we'll measure this in a moment and write down the torque radius. But I want to just point out, if you take then R to be the torque radius, or the lever arm, and since we're hanging a little weight, the force is the weight of the object, so there's mg. And if you just, of course, change the order, this would be the torque. And so that's going to be an important number. It's not going to change here in part 1, because we're going to always hook up the same mass to the same torque radius. And so that's why your author here on the table just has you write it one time up at the top of the table. So I'll put that here. And so here's the capital R equals, so that's the torque radius. And then your author has the torque is equal. And so this is how we're going to calculate that torque. Or I should say how you're going to calculate the torque. I will just do the measurements. So I will measure this radius. And I will point out that this mass is 20 grams, but you are asked to put your mass in kilograms. And then, of course, these other two you will know, because I'll measure that one and you know that one. Although I want to talk more about that one in just a second. And the final equation, and it's a bummer I didn't give myself quite enough room. That's okay. I'll put the fourth equation right here. Says, here's how you find the moment of inertia, or the rotational inertia. You take the torque and divide it by the angular acceleration. Now again, if that one doesn't look familiar, let me write it as we saw it in class. We called this Newton's second law of rotation. This says torque is equal to the rotational inertia times the angular acceleration. And so if you just rearrange it and bring the angular acceleration, you can get the moment of inertia. That's why, coming over here to part 1, the last of your calculations are right here. This is what we're hunting for in part 1. We're hunting for what is the rotational inertia. And so this last step would be to take the number up here for the torque and then divide it by whatever angular acceleration you have, and that will give you your rotational inertia. Now, if you look at the table, there is a lowercase r. There's even a lowercase r squared, more on that in a minute. But you'll see here a 3, a 6, a 9, a 12, a 15, an 18, a 21, and a 24. And this lowercase r is the distance that those square weights are from the rotational axis. Well, that's why I was saying earlier, be careful not to confuse in this discussion the capital R with the lowercase r. Maybe I'll put in the squares also. 9, 36, 81, 144, 225, and I guess I don't know what 18 squared is. Looks like it's 324, 441, and 576. Okay. So those numbers are given, but I'll say it again. This lowercase r is the distance, and I'll just walk over to the equipment again. The lowercase r is where these are. And so you can see in that chart, we're asked to move them out further and further and further and further and further. And the last distance way out here is the 24. That's as far as we could go. And so we're going to try to see, as I said, if the moment of inertia is increasing, decreasing, or staying the same. And as I've already told you, it should be increasing. And it should be increasing in relationship to the square. So we'll do that with our graphs, and you'll begin to see why they have this right here, the little r squared here. So again, there's quite a few calculations. So if I could summarize this real quickly, it's going to be this. It's going to be you and I together in a moment will measure the height and the time for these cases 1, 2, 3, 4, 5, 6, 7, 8 times as we move the weights out further and further and further. And then after a series of calculations, we should see the moment of inertia changing. And since it's moving out, we should see them getting bigger. And we should see them getting bigger in proportional to the square of the distance. So soon we will make a plot in relationship to the square of the distance. So let's see what we ultimately get. But it's going to be your job then to calculate this column, and this column before you can do your graph. So that's the part I'm going to leave you to do. You're going to do the calculations. But just to kind of summarize, here's how you get the A. You get the A using these two pieces that I'm going to measure for you in the first equation. You put in the H, you put in the T, don't forget the 2, you get out your calculator, you get the A. Then once you get the A, you can divide that by the R to get the alpha.
Radians.
Huh?
In radians.
And yeah, I'll talk about the units here in just a second here. Hang on. And so we're going to put this right there. That's going to be the R. And so I'll measure that in just a second. And so then you will get this angular acceleration. And then, of course, this last equation is going to let you get the moment of inertia by taking the torque and then dividing it by the alpha, which is why you got to do this calculation. And actually, maybe I'll do this one with you. So I'll do this one with you, and we will actually put that right here in our table. And then once we have it, to get this one, we just divide by this column, and we will fill this in. Now, the units here can also be a little bit confusing. And so if you look carefully at yours, you will see that your author asks you to measure, and this isn't a surprise, time in seconds, He also asked you to measure mass in kilograms, and I don't think that's a surprise. That's why I said earlier, why don't I write this mass in kilograms, even though I said it earlier in grams, but we should calculate it in kilograms. But here's the part that might throw you off. He asked you to calculate and do the units of distance in centimeters. So that's not the standard meters that we usually did in class. He also then says that the angular acceleration then is to be done in radians per second squared, not degrees and not revolutions. So coming over to here, let me put this into our table. So you'll see that he says height in centimeters, and that's what I was saying. We're going to measure everything in centimeters, not the traditional meters. Time will be in seconds, that's kind of normal. But what that means then is we will get an acceleration in centimeters per second squared. It also means we will get an angular acceleration in radians per second squared. Now, fortunately, these units will work out just fine as long as you've measured your height in centimeters and your time in seconds. So don't be too concerned about these. Just follow the formula and plug it in, and these will work right. It then will say that your moment of inertia will come out as kilograms and then centimeters squared. And if you remember from class, I said the unit for rotational inertia was kilograms per meter squared. And of course that's because we use meter, not per, times, kilogram times meter squared. But we're not going to do that. We're going to go kilograms times centimeter squared. So this is a long way of saying that we got to be a little careful with our units. It's been formatted in centimeters, and that will match the numbers on our graph. I was tempted to change it, but then I got to looking at the graphs and I said, oh, well then the graph formatting would all be off. So we're going to stick to what the author said, measure distance in centimeters. So even though it's a little bit, I'll call it abnormal, there's nothing wrong with it. It's just different. And it's actually pretty easy to measure things in centimeters in the lab. So I'm sure that's why the author of your lab manual set it up. But I do think it might be a little better if it was the same setup that we're doing in lecture and the same setup your textbook is doing. But maybe there's something educational about that. That's saying, hey, you could do it either way. Your distances could be anything you want. Just remember, if you do centimeters instead of meters, then you're not going to get things like energy in joules and force in newtons. There would be other names we could give to it. I'll stay away from those other names, but they would just be different. So not wrong, but different, and not the I'll call the normal here. All right, so with that in mind, I think we're ready then to begin the actual lab, to actually begin to fill in this table. I'll start with the easy one first. Let's just find this radius. So coming over to here, and that means I probably need to remove the string so I can get a measuring device in here. So let me just pull on this string here and kind of get this out of the way for a second. And let me get the radius. And I have this nice little instrument. It's called a caliper. And I can open it up. That kind of turns it on. And this little opening here measures the size of it. It does measure it in millimeters, so I'll be careful with that. And so I'm going to come over here and open up the jaws here and close it up. And then take a reading. And I know you couldn't see this on the camera at this angle, but it says 37.65. Now, I'll leave it there for just a second, and I'll come over here, and I'll grab my calculator, because if I type in 37.65, I need to remember, first of all, that's millimeters, and they want me to write it in centimeters. All right, so the thing to do is to divide that by 10. since they vary by a factor of 10, right? There's 1,000 millimeters in a meter, and there is 100 centimeters in a meter. So they differ by 10. Okay, so this says that it's 3.765. But now remember, if you look at the way I did it, that's the diameter. So let me go divide by 2 and put then 1.88 centimeters. So there is what your author calls the torque radius in centimeters. So the reason I decided I should help you with this calculation for torque is the units can also be a little confusing here. As we mentioned, the author asks us to put in units of mass in kilograms. And I already pointed out that I told it to you in grams, but I'm going to put it here in kilograms. Good. Here's the one I want to make sure you don't mess up on is the G. We in class have been saying G is 9.8 meters per second squared. And that's true. But remember, this lab wants it in centimeters. So let me put 980 centimeters per second squared. And that could have easily been overlooked, even though I said, hey, make all your distance measurements in centimeters, not the traditional meters. Okay, and then the last piece, the R, is the 1.88 centimeters. And so if I put all those together, 0.02 times 980 times 1.88, I get a number of 36.85. And as I said earlier, weird units, right? Because in class we said this was a Newton meter, but it only comes out to be a Newton if you measure distance in meters, and we didn't do that. So what we have is we have a kilogram, and instead of having meters squared, we have centimeters squared, and then of course we have seconds squared. And that doesn't have its own name, that's just what we'll call it here. And so coming over here, I will put 36.85 kilograms centimeters squared per second squared. And let me just check, it hopefully matches, yeah, the units that your author has put. So no fancy name. Certainly don't call it a Newton meter like we were doing in class, right? We would only get a Newton if distance was measured in meters, mass in kilograms, and time in seconds. And we do have kilograms and seconds, but we don't have meters. So again, got some oddball units here. So like I said, I wanted to do that calculation here. And like I said over here, you're going to need that number because to get the rotational inertia, you got to take that number we just calculated, that 36.85. So this is going to be 36.85. And we'll divide it by our angular acceleration, which we get from our linear acceleration, which we get from the height and time. So I'm going to have you fill in the rest of this table. I'll go ahead and work with you to get the heights and time. All right, so let's start with the first one. The first one means I got to put this string back on here. So let me lower this down here. Let me take the calipers off. Let me hook the string on. There's a little notch there. Let me spin it around. And as we already set up earlier, the square weights are 3 centimeters out. That's the first one in our row up there. And so I'll hook up my weight. And just to have something kind of consistent, I'm going to pick a height of 80 centimeters. And careful here, my string just went on the wrong pulley. So let me wind up the string on the correct pulley. And I'm going to adjust this little weight so that it is always dropping down 80 centimeters. Okay, 80 centimeters. Maybe I'll turn it that way, 80 centimeters. Okay, so let me reach over here and grab my stopwatch and turn it on. Clear it. Okay, so the height is going to be 80 centimeters, and let's see how much time that takes. And so 1, 2, 3, go. And so this takes a little while to collect the data. And remember, the weights are in close, so this is going to be the fastest one. But I'll just wait till it gets to the bottom here. Stop. All right, so coming over here to my chart, I have a height of 80 centimeters and a time of 16.67. And let me say it a third time. Let's have you then do the calculation, get the translational acceleration using the first equation, and then using the second equation, get the angular acceleration, and then get the rotational inertia using the fourth equation. And I'm going to go ahead and just fill in 80, unless something weird happens. I'm going to always set these at a height of 80. All right, so let me go to the next one. All right, so the next one, to wind this up again. Oh, and maybe I should have done this before I wind it up, but that's pretty close. I need to now move the weights out so that they are 6 centimeters out. And hopefully you'll see right away that this is going to be, slower to unwind. And the inertia of it is a little bit more. That's the whole point here. And so grabbing my meter stick again and setting it as carefully as I can at a height of 80. And 1, 2, 3, go. It should unwind. And I'm hoping, as I said, that this will take a little bit longer. That means it's harder. It's got more inertia. Ready, stop. All right. And so I'll write this one on the board. And so 17.85. And sure enough, it took a little longer. All right, well, let's try the third one. And I'll move the weights out. Okay, so now let's move them out to a position of 9 centimeters. So they're a little further. Let's wind up. Oh, the string. Looks like the weight came off and the string went on the wrong pulley here. And so I'll just kind of wind that up. And take the little weight and hook it onto here. And let me find the same height, because it really wouldn't matter if it's the same height, but I already wrote 80 in my table. Okay, so there's the 80, and 1, 2, 3, go. And we'll just let it unwind here. And again, conceptually, hopefully we will see more time that this is harder to get it to rotate now that the weights move out. And that's really the big lesson. But now we'll see a pattern, stop, where the pattern is that it moves out in proportional to the square. All right, so here I have a time of 19.34. So again, get out your calculator and measure those. And I think you're going to be seeing this number getting bigger and bigger. And eventually we'll see the pattern when we do some graphs here. All right, move them out again. Let's see. So we're at 9. Let's go to 12. So 12, 12. Wind it up. And set the little weight again at a height of 80 centimeters. Okay, so there's 80 centimeters right there. Grab my stopwatch and 1, 2, 3, go. And so again, it begins to unwind. And I think you could even just see visually that it's harder to get it to go around. It has less of an angular acceleration. It's sluggish. And you'll see that in the time. And stop. And so I got a 21.15. All right, let's keep going with this. All right, so 12 now comes a 15. So we'll move it out even more. And wind up the string. It up, set it at our magical 80. There we go. Grab the stopwatch and 1, 2, 3.